today we will be starting with the next section of physics, which is Newton's laws of motion. So let's start with the statement of the three laws. So the first law states the property of inertia, or it is also called the law of inertia. Whereby every body or every mass has a certain property, whereby it wants to continue in a state of rest if it is initially at rest, or continue in a state of motion, uniform motion if it's already in motion, until and unless it is acted upon by an external force. So that particular property of it, of the body to want to continue in its state, that property is called the property of inertia. So the statement of the first law, or the law of inertia, is that any body at rest or in a state of uniform motion has a tendency to continue in its state unless and until by an external force. So this is called the property of inertia. This tendency of the body to continue in its state of rest or continue in its state of uniform motion, whichever be the case, that is called the property of inertia. So just make a note of this definition of Newton's first law. Okay. Right, so I'm sure you're familiar with the statement of first law from a number of places. Okay. Now we will see that this property of inertia can be divided into two categories. Okay. Inertia of rest. So if a body is at rest, it will continue to be at rest unless and until external force acts on it. Okay. So this property is called inertia of rest. For example, you have a smooth surface and you have a block lying on it. At rest. its mass is m. So the mass m is the inertia property. The larger the value of m, the more inertia it possesses. In its state of rest. So now we know that this will continue to be in its state of rest until and unless some external force acts on it. Now it's at rest initially. Now suppose an external force starts acting on it, and as a result of the application of this external force, at some time t, the same body has now gained a velocity v because of this force acting on it. So we can see that on application of horizontal force F for time t, what happens is that the acceleration becomes F by m. So the velocity, which will become at, will become F by m into t. So you can see that the velocity is inversely proportional to the mass. So the larger the mass m, the greater the inertia of the body, or the tendency to resist change in its state of rest. The effect of force is inversely proportional to the mass of the body. So we say, as far as inertia of rest is concerned, it is the mass which is the property which represents the inertia. जितना ज़्यादा mass होगा, उतना ज़्यादा inertia होगा. The more it has a tendency to resist the change in its state of rest on the application of external force. So that particular property is called the inertia of rest. Similarly, we see next that there's a property of inertia of motion. So just take down this example. Yeah, let everybody write down this for me, then I will scroll down. No, there's no particular formula. Inertia is more like a property. Yeah, so when we talk about inertia of rest, it is a measure of the mass. But inertia of rest is not the only type of inertia. There's also inertia of motion. So I'm coming to that. Okay, so understand this through this example. Okay, now similarly, we also have the property of inertia of motion. Let's understand what that is. So imagine we have this time a body of mass m, which is already in a state of motion. It's moving with a velocity v0, let's say, at time 0 on a smooth surface. So a block of mass m moving at a velocity v naught at the initial time t equal to 0. It possesses something called momentum. We define momentum as mass into velocity. Now you see, for example, to bring this body, which has a momentum p equal to mv naught at t equal to 0, to rest in a certain time t, force needs to be applied. Because this body otherwise has a tendency to continue in its state of motion until and unless this body has a tendency to continue at uniform momentum or in a state of uniform motion. Okay. Until and unless some force needs to be applied. So force needs to be applied to change its momentum. So this property is again called inertia of motion. So for example, to bring this body to rest in a certain time, force needs to be applied such that this is what will happen. If it was moving at t naught at time t equal to 0 on this smooth surface, और अब उसको to bring it to rest, I start applying a force in the opposite direction. Then the block might come to rest. Its velocity might become 0 at some time t. Provided what will happen is that the deceleration E will be equal to F by M. So final velocity is 0 should be initial velocity minus deceleration into time. So A should be equal to V naught divided by T, or F by M should be equal to V naught by T. Or the amount of force I need to apply is again mv naught divided by T. You can see, to bring the body which had initial momentum P equal to mv naught to rest in time T, the force needed is equal to mv naught by T. So the force is directly proportional to P, the initial momentum. So this property of the body to resist change in state of uniform motion is called inertia of motion, and is represented by its momentum. Therefore, the larger its momentum, the more its inertia, but inertia of motion. So that's why I said that inertia is not necessarily represented only by mass. If you're talking about inertia of motion, it is also represented by its velocity, or the product of mass and velocity, which is called linear momentum. Okay, understood the point, Dhruv and Tejas. So inertia is more about the property. It cannot be represented by a single formula or a single function. But yeah, if you're talking about a body at rest, then its inertia of rest is represented by the mass of the body. Jitna zyada heavy hoga uska mass, the more inertia it has. On the other hand, if a body is already in motion, then it has the inertia of motion. It has a tendency to oppose any change in its state of uniform motion. So that tendency to oppose the change in state, or the inertia of motion, is measured by its amount of momentum. The more the momentum of the body, that is, the more the product of mass into velocity, the more this tendency of its inertia of motion. Okay. So, for example, a heavier body can have more inertia than a lighter body. It can have even less inertia than a lighter body. But for it to have, if the lighter body to have more inertia, it has to move at a larger velocity. Proportionality means relationship. Proportion is relationship. Like we say, momentum is mass into velocity. So momentum is proportionate to the mass of the body. It is also proportionate to the velocity. It has a relationship with velocity. We increase the velocity, momentum will also increase. If we increase the mass, momentum will also increase. Yeah, that is true, Anushka. But suppose we are comparing the inertia of two moving bodies. So एक का momentum है m1v1, दूसरे का momentum है m2v2. So whichever one has more momentum possesses more inertia. So that's why I said that it's not necessary that only a heavier mass has more inertia. Okay, if a lighter mass is moving at a larger velocity, it has more momentum, so it has more inertia of motion. Okay, understood the point. So if you are comparing, for example, a body of mass m1 of let's say 1 kg, but moving at a velocity of let's say 50 meters per second. On the other hand, you have another body of mass, let's say 5 kg, but it's moving with a velocity of only let's say 4 meters per second. So which one has more momentum? The first one has momentum of m1v1. So it has a momentum of 50 kilogram meter per second. The second one has a momentum of m2v2. So that's only 20 kg meter per second. You can see that therefore the first one has more inertia due to its motion compared to the second one. So if we want to stop both the bodies in a time of let's say 2 seconds or something, we have to apply a larger amount of force on the first one compared to the second one. So in that case, we'll say that the first one had more inertia than the second one. Okay. So that's what I mean by saying that it also depends on mass, because then you can compare the inertia of two different bodies. Good, very good, Beta. Okay, so as we do more examples, Vanchika, these all these concepts will become more clear. All right, so that is Newton's first law. It just outlines that there is such a property just from inertia. So the inertia comes in two categories: inertia of motion and inertia of rest, which you just understood by these two examples. Now the second law, which I'm sure all of you have heard, which is the most famous law, it is the law of force, or it outlines the concept of force. The exact statement of Newton's second law is that the net external force acting on a body equals to the rate of change of its inertia. Rate of change of its momentum. We read this like this, that the net external force equals to delta P by delta. This is the proper statement of Newton's second law. You might have heard it as F is equal to ma. That is an equivalent statement under certain conditions. Okay, but the proper statement is actually this one, that the net external force is equal to the rate of change of momentum, where F net is the net external force. Okay, or that means it is the sum of all forces acting on the body. And what we mean by sum over here is vector sum. Because remember, force is a vector quantity. We have discussed a little bit about vectors before. Okay. And on the other side, delta P by delta T, this is change in momentum divided by the time interval. It is nothing but rate of change of momentum. Where momentum, of course, we just understood earlier, is equal to mass into velocity. Okay, so just make a note of this. Oh yes, Yuvraj, I'll scroll up just a second. Okay, guys, we'll come back to the second law. Just a minute. Somebody has to, Yuvraj has to note down these things. So I'll just come back to the second law. Just give me a moment. Okay, let's come to this now. So always remember the proper statement of Newton's second law is not that F is equal to ma or force is equal to mass into acceleration. It is that the net external force, that is the sum of all forces acting on the body, the vector sum, that is the net external force, and that equals to the rate of change of momentum of the body. So when we do a couple of examples, this will become more clear to you exactly how we calculate rate of change of momentum. Okay, so one thing you have to understand over here, momentum is expressed in kilogram meter per second. That is the SI unit of momentum. Therefore, delta P by delta T is expressed in kilogram meter per second square. So, the SI unit of force, which we call Newton, is such that 1 Newton kilogram meters per second square. Because F is equal to delta P by delta T. So in SI unit, 1 Newton here will be change in momentum in SI unit, which will become 1 kilogram meter per second in a time of 1 second. So that will become 1 kilogram meter per second square. So that is the relationship. Yes, kg meters per second square can also be written in newtons. So that is the equivalence between them. Okay, that 1 Newton is equal to 1 kg meter per second square. This is the standard international units. Now similarly, we'll discuss the CGS unit also. Okay, so let us understand this now. The next thing, CGS units. CGS system of units is one where mass is expressed in gram, okay, length is expressed in centimeters, and time is expressed in seconds as you know. Okay. So therefore, CGS unit of momentum is gram centimeter per second. Okay. CGS unit of force is given a special name, it is dyne. Okay. So again, because F is equal to delta P by delta T, so it means that one dyne of force equals to 1 gram centimeter per second per second. So 1 dyne equals to 1 gram centimeters per second square. So this is the relationship between the CGS unit of force. Okay. Also from this we'll see 1 Newton, which is 1 kilogram meter per second square, can be expressed as 10 raised power 3 gram into 10 raised power 2 centimeters per second square. So that is 10 raised power 5 gram centimeter per second square. So that is equal to, so 1 Newton equals to 10 raised power 5 times. So this is the relationship between the SI unit and the CGS unit of force. So before we get into numerical examples where we'll have to use units properly, make sure you understand the SI and the CGS units and the relationship between the SI and the CGS units. SI, as you know, stands for Standard International Units. In the Standard International System, length is measured in meters, mass is measured in kilograms, and time is measured in seconds. Yes, Adinath, so 1 Newton equals to 10 raised power 5 times. That is correct. That is 0.1 million, you can say. 1 Newton is 1/10 of a million, because a million is 10 raised power 6. Yeah, it is called the alternate unit in the CGS system. So any physical quantity can be expressed in various different systems of units. Now the two predominant systems of units are the standard international, which is the preferred system of units, and the CGS system, which is the second most preferred system of units. There are also other unit systems like the old British metric system, in which length is measured in feet or inches, right? Yes, MKS is another system. Then the old British metric system, or what is called the FPS system, the foot pound second. So mass is measured in pounds instead of kilograms, and distance or length is measured in feet, or sometimes even yards. So there are different types of systems of units. But in our study of physics, the two predominant important ones are the CGS and the SI systems, or the standard international and the centimeter gram second systems. Yeah, 1 pound is roughly, it's like this, that 4.5 kgs is 10 pounds. 4.5 kg is 10 pounds. LBS is the symbol used for pounds. So 1 pound is 9/20 kg. Or 0.45. Like that, approximately 3 feet is 1 meter. Something like that. Alright, let's come to our first numerical example. So at t equal to 0, this body has an initial velocity of 20 centimeters per second, and its mass is 50 grams. Now, by the time it is 10 seconds, its velocity has increased to 30 centimeters per second. Obviously, the mass is same, it's 50 grams. And this has happened under the action of a force F. So we have to find the change in momentum, delta P, of the body from 0 to 10 seconds. And then from that, calculate the force F acting on it in SI unit and in CGS unit. And assume that this is a smooth surface. Just work this out, people. Yes, that's correct. Dhruv, that's correct. Yes, Aparna, correct. Very good. Adinath, correct. Nee, Adinath, your second and third part is wrong. Your change in momentum is correct, but then you have to divide it by time. Na? Time is only 10 seconds, beta. Yes, Dhruv, correct. Yes, Adinath, correct now. Good. Okay. All right, so let's see. So the initial momentum at t equal to 0, let's say p1, that initial momentum is mu. Okay, so that is 1000 grams centimeter per second. Okay. The final momentum at t equal to 10 seconds, let's say p2, is mass into final velocity. So that was, okay, because mass was 50 kg, sorry, 50 grams, and initial velocity was 20 centimeters per second, final velocity was 30 meters per second. Alright, so first thing, change in momentum delta p is final momentum minus initial momentum. So that is 1500 minus 1000, or 500 grams centimeters per second, or you can now write that as 500 into 10 raised power minus 5, or that will become 0.005 kilogram meter per second. So we can express it either like this or like this. Okay. So that is the change in momentum. So second thing, the force is going to be rate of change of momentum, delta p by delta t. So that is 500 grams centimeter per second divided by 10 seconds. So that is 50 dynes. Okay. Or that is the same thing as 50 into 10 raised power minus 5, or 5 into 10 raised power minus 4 newtons. So this is in CGS unit, this is in SI unit. नहीं बेटा mass into velocity है ना. So see the final momentum P2 is m into v, so that is 50 grams into 30 centimeters per second. Okay, so it's 1500 grams centimeter per second. So that is the same thing as 1500 into 10 raised power minus 5 kg meter per second. Because 1 gram centimeter per second is 10 raised power minus 3 kg into 10 raised power minus 2 meter per second. So that's the conversion. Okay, na? Arav. So anyway, just minimizing this for you. Make sure you are clear with all the units and systems. Okay, people, so hope this is clear. Okay, now let's look at another question. Now suppose we have this situation that once again we have a block on a smooth horizontal surface. (25 kg) block. So this is at rest initially. Block. But now two people start. So one guy starts pushing it with a force F1 and the other guy is pushing it with a force F2 in opposite directions. So say Amit and Mohit start pushing the block as shown above. Okay, I'll explain, Vanishka. At constant forces, horizontal forces of F1 equal to, let us say, 8 newtons and F2 equal to 3 newtons. So find the velocity of the block when its displacement is 20 centimeters. Okay. And time taken for displacement of 20 centimeters. How much time does it take to reach a displacement of 20 centimeters? So this is the next question we have to do, where you have to apply a mixture of the concept of Newton's second law that we just learned and of course kinematics from before. Yeah, now Vanchika, the quantity delta, it means change. Okay. So for example, delta x means change in x. So it is the final value of x minus the initial value of x. Okay. So similarly, delta p means it is the final value of momentum minus the initial value of momentum. Like that. Similarly, delta t means change in time. So it means the time interval. Okay. So if I ask you what is delta t from 12 to 12:15, so it is 15 minutes. You understand, because the final time is 15 minutes more than the initial time. Okay, so just work out this question, people, and get the answers in SI units. Okay. Get all the answers in SI units in this. Okay, so yes, Aparna, your answer is correct. Yuvraj, your answer is also correct. Okay. Aparna, you use the approximation, root 2 ka value leke. Good. Okay. So let's see how we'll apply. Bhaumik, you have to check your answer again. So let's first of all check how we'll apply Newton's second law. Okay. So here we say that net force. Okay, this is the sum of external forces. Okay. So on the body, यहाँ पे क्या हो रहा है? One force is acting like this in this direction. The other force is acting in the opposite direction. So what is the net force? It is going to be F1 minus F2. But the magnitude of the net force is going to be the difference of the two forces because they are acting in opposite directions, right? They are pushing in opposite directions, and the magnitudes of these forces are 8 and 3. So you can see that the net external force will become 8 minus 3 or 5 newtons. Okay. So now you come to the statement of Newton's second law that net external force will become equal to rate of change of momentum. So in this, 5 newtons is equal to rate of change of momentum. Okay. Now you come to the kinematics part. So this body of mass m is at rest at t equal to 0. Now after some time, which we don't know, but the velocity becomes v, and during that time the displacement from here to here is some s. Okay. So that displacement is given to us as in the question. That displacement is given 20 centimeters and the mass of the body is 25 kg. So this displacement is 20 centimeters and the mass of the body is 25 kg. Okay. So in this, delta p by delta t will become mass into final velocity minus 0 upon time. So it will become mass into v by t. Okay. The left hand side of the equation will become this. So that is nothing but mass into acceleration, because acceleration is delta v by delta t. In this case, it is v by t. So now we know that the left hand side is mass into acceleration, and the right hand side, the net force is equal to 5 newton. So equating the, sorry, this is the right hand side, that's the left hand side, my mistake. So the left hand side of this equation is this, and the right hand side of this equation. So LHS equals to RHS is telling us that 5 newtons is equal to 25 kg into some acceleration. So the acceleration is becoming how much? 1 by 5 or 0.2 meters per second square. Okay, so this is what we are getting finally, that the net force of 5 newtons acting on a body of mass 25 kg is producing an acceleration of 0.2 meters per second. Now the rest is kinematics. So you can see that u is 0, s is equal to 20 centimeters or 0.2 meters. Acceleration is 0.2 meters per second square. So velocity we want to find out, use the relation that v square is equal to u square plus 2x. So here v is equal to square root of 0 plus 2 into a, which was 0.2 into 0.2. So 0.2 root 2. So that is approximately 0.2 into 1.4, or approximately 0.28 meters per second. That is the velocity. And use the relation v equal to u plus at, or s is equal to ut plus half at square, whichever, to get the time. So here this velocity of 0.28 is 0 plus 0.2 into t. So the time comes out to be 1.4 seconds. Or you use this, that the displacement is 0.2 meters. That is so whichever method you use, this is the value of the time and this is the value of the velocity. But in what unit, beta? Arav, you have to express, you have to tell me in what unit you got the final answer. Then I can tell you whether it's correct or not. I have done everything by converting to SI unit because the question clearly said get the answers in SI units. But in serious units, see what the answer will be. The velocity, which was how much? The 0.28, na? So it will become 28 centimeters per second. In CGS, V will be 28 centimeters per second. So make sure you do the conversion correctly, okay, people. Okay, so hope this is clear to all of you. Okay, good. Next, let's look at another example question. So in this example, now we have one of those industrial conveyor belts. this is so an industrial conveyor belt of very long length. Assume that the length is very long, it's going very long on this side, is moving at a constant speed of v naught equal to 2 meters per second, while concrete is dropped onto it at a uniform rate of 5 kilograms per minute. Okay, so this is concrete over here. So it's being dropped through a pipe. So the conveyor belt is laden with concrete now, but it's being dropped at the rate of 5 kilograms per minute. This is per minute. So find the change in momentum of the conveyor belt in 10 minutes. In 10 minutes, how much does the momentum change by? And second, the net external force acting on the belt applied by the rollers below it. So the belt is moving on these rollers, and to keep it moving, the rollers are applying force like this. By rotating like this, these rollers are fixed rollers, and they're rotating like this and applying a force in this sort of direction. So what I'm asking is that these rollers, they are applying force in this sort of direction. So what is the net force that is acting on the belt as a result of the rollers as it is moving? Okay. So this is a slightly different type of application of Newton's second law, but you will see again it can be solved very easily by just using the definition. Conveyor belt. Conveyor belt is a belt that is used to move mass from one position to another. Like you have seen in airports now, like the luggage moving belt in an airport, for example. That's an example of a conveyor belt. So as this moves, put a piece of luggage here, it keeps moving around with the belt. That kind of thing is called a conveyor belt. Hello. Yeah. Yes, Aparna, correct. Yes, Yuvraj, to answer your question, inertia is a property, not so much as a physical quantity. Momentum, if you express inertia in terms of momentum, yes, it has a unit. Okay, but inertia is more the property of the body. We say it's a tendency of the body to change, to oppose a change in its state. That thing is called inertia. So we don't really express it in terms of unit and magnitude. Rather, momentum or mass, these kind of things are expressed. Yeah, Aparna, your answers are correct. I'm just waiting for the others now to. Okay, so see people, how we'll do this question. We understand that at some particular time, some particular time t, let's say the mass is m. But remember, mass is also being dropped onto this. So at a time later, T plus delta T, the mass is increased to m plus delta m. What is happening at time t? The momentum is some mass into velocity, but at delta t later, the momentum has become, let's say, p prime, which is m plus delta m into v naught. Where in this, what is happening is delta m is the mass added in time delta t. So the change in momentum delta p is the momentum at the final instant minus the momentum initially. So the change in momentum is nothing but the added amount of mass into velocity. So this is one very important relation. So from this you can see the first part of the question, you want to find the change in momentum in 10 minutes. So that will be nothing but equal to this, where delta V will be the mass added in 10 minutes. We want to calculate this. This will be this. So delta M will be equal to how much? It will be, how much was it? 5 kgs per minute, right? Yeah. So the mass is being added at a rate of 5 kgs per minute multiplied by a time of 10 minutes. So 50 kgs is the mass that has been added in 10 minutes. Okay. Because this delta M will be the rate at which mass is added multiplied by the time. That's what. So the change in momentum will become 50 kg multiplied by the velocity, which was 2 meters per second. So the change in momentum will become 100 kilogram meter per second in that interval of 10 minutes. Okay, so that's the answer to the first part. So just go through this and make sure you understand this properly first. Then we come to the second part about the force. Okay, people, so understood this, got this. Now the second part, the net force acting on it, that is rate of change of momentum with respect to time. Now earlier we had seen in this equation here that change in momentum is given by this. Okay. That delta P is equal to delta M into V naught, where delta M is the mass added in time delta T. Okay. So this becomes delta M V naught divided by delta T. Now in this you can see that delta M by delta T is nothing but the rate at which mass is being added. Okay, because delta M is the change in mass, so change in mass upon change in time is nothing but the rate at which mass is being added, which was given to us as 2 kilogram per minute, or whatever, 5 kilograms per minute. This was given to us in the question. Given. So therefore, and V naught was of course given 2 meters per second. So the net force is becoming 5 kilogram per minute into 2 meters per second. Okay, so we will now convert this to 5 by 60 kilogram per second to get in SI unit. Okay. So as you can see, that will become 1 by 6 kilogram meter per second square, or 1 by 6 newtons, or approximately okay, this will become the net force. Okay, so is this example clear to all of you people? Good. Okay. Now let's move on to another interesting aspect. Okay. So from these things we'll first write down the final part, 1/6 newtons you're getting. Yeah, so rounded off it is 1.167, no problem. It is rounded off, and that's why I said approximately. Correct, it's a non-recurring, non-terminating decimal, but you can round it off like this. Okay, now through these examples, we'll understand another aspect of Newton's second law. That when we say net force is equal to rate of change of momentum, okay, where momentum is mass into velocity. If mass m is constant, any rigid body, that's what's happening. Like that block that we considered in the second example or the first example, then change in momentum upon change in time will just become mass into change in velocity upon change in time. Now see what is happening, delta P will be change in mass into velocity, but mass is constant, so it will become mass into change in velocity. So therefore, delta P by delta T will become mass into change in velocity upon change in time. Okay. So this is the concept. And we know that rate of change of velocity is nothing but acceleration. Rate of change of velocity with respect to time is nothing but acceleration. So in that case, we can say that the net force is equal to mass into acceleration. But this is provided mass m is constant. Okay. So this becomes what we call a conditional statement. This is a conditional statement for Newton's second law. The condition being that mass is constant. Whereas the general statement is this one. The general statement for second law. It is independent of any special condition. That is, mass may or may not be constant. Velocity may or may not be constant, but this definition will always apply. Whereas this definition is subject to the special condition that we are applying Newton's second law to a rigid body or a body whose mass is constant. One of the properties of any rigid body is that its mass is constant. But obviously a conveyor belt is not a rigid body if mass is constantly being dropped onto it. The condition is that mass is constant for the conditional statement. Constant, beta. Bhaumik, that sentence says that mass is constant. This condition is mass m is constant. Right. So hope this is clear. Whereas the other example we took of the conveyor belt was that is like a reverse kind of situation. वहाँ पे क्या था? The velocity was constant, but mass was varying. So on the other hand, for a system like a conveyor belt, moving at constant velocity, v naught, but with mass changing at the rate delta m by delta t, we saw that net force became delta m by delta t into that velocity. It became like this. And you just seen this in the previous example, how this happens. So this is when velocity is constant, but mass is variable. This is the opposite of this situation. This is when mass is constant, but velocity was variable. Now, it can of course happen that both are variable also. Okay, but here it is seen two cases where one of them is constant, the other is variable. But the point is that this equation will apply to both. This equation will apply here also correctly. This equation is applying in this equation also correctly. So it is a non-conditional statement. It's a general statement of Newton's second law. Okay, so finish writing down this part, people. Okay, so let's look at another interesting question based on all this now. So next example, we this time have a rough surface. So it generates friction, and on that surface Dhruv will discuss. We'll discuss that kind of situation where both mass and V are variable. Don't worry, we'll discuss about that. So this time we have a mass of 100 kilograms. Now it's being pulled by force F1, which is of 40 newtons, and also being pushed from the other side by a force F2 of 10 newtons. Okay. Now what is observed that the block starts from rest. Okay. At time t equal to 0 with constant forces F1 and F2 acting on it, such that after 1 second its displacement is 4 meters. So find the frictional force in newtons acting on it. Just try out this question, people. Okay, anybody got the answer? So just to give you a hint here, how you have to proceed. So they go on the block, what is happening? Apart from the two external forces that we are applying, there's also friction that the ground is applying, which will be opposite to the direction of motion. Yes, Yuvraj, that is correct. No, 1 second में ना 4 meters. So acceleration will be something different with that. Just do your calculation again. वो अपन ना 750 न्यूटन से तो कम होगा. It's too much the amount of force you're saying. Okay, so if this is friction, friction is going to act opposite to the other two, because the other two are creating the motion along this direction. Now let's say under the action of all these forces, the body has an acceleration E. So net force should be equal to rate of change of momentum here. That should become m into E, because mass is constant. That's a rigid body. So net force will be how much here? It will be F1 plus F2 minus friction. So it will be 50 minus friction is equal to 100 E. That is the first thing. Then the second thing you will see here, that since displacement is equal to 4 meters in 1 second, is starting from rest. So half E into T, which is 1 second square, should be equal to displacement, which is 4 meters. So E is becoming how much? 8 meters per second square. Oh, sorry, my mistake. People, I made a mistake here. Okay. Acceleration can't be 8 meters per second square. There isn't enough force. Okay. So just change the value. It was the other way around actually. My mistake. After 8 seconds, the displacement is 1 meter. It's not 1 second and 8 meters. It was like this. Sorry, it is 4 meters. After 4 seconds, the displacement is 1 meter. See, logically it's not possible. No? The force is less than 50 newtons. So how can you get an acceleration of 8 meters per second square? You need a lot more force for an acceleration of 8 meters per second square. So anyway, so in 4 seconds, the displacement is 1 meter. Okay. So the acceleration is becoming 1/8 of meter per second. Or the acceleration is becoming 0.125 meters per second. Yes, now it is correct. Understood now why 8 meters per second square would not have been possible, because there are net force 50 se kam hai. So how can the acceleration become 8? You know? So this is your second equation. Now substitute this in the first equation. So you will get friction as 50 minus 100 E. that will become the amount of frictional force. So make sure you mark the correction in the data of the question. It was supposed to be 4 seconds of time the displacement is 1 meter. Instead of 1 second of time the displacement of is 4 meters. By mistake I interchange the values. Anyway, so hope the question is clear to all of the people and you understood the method of solving. Okay. So please continue reading ahead of the Newton's laws chapter from physics part 1 module and work out some questions from the exercises also, and we'll discuss more in the next lecture. Plus we'll do some exercise problems also. And of course we have to do the discussion of Newton's third law to complete the theory part itself. Okay. So that's it from today from my lecture people. Make sure you revise the lecture notes and try out some questions from the module exercises. Okay. Wish you all the best. Okay, thanks people. Good afternoon and see you next time.